Apparently I've already exceeded my cloud storage, but it lets me record still, so I'm kind of like, what happens next? I don't know. Is it gonna charge me? I don't know. We'll see. There we go. I'm sharing my screen. I'm recording. Things are good. Okay. Start a note here. You guys are my Monday, Wednesdays. In my class this morning, I had 2 people join in to the meeting from home, so that was good. But one of them somehow got their audio on and was calling Scotiabank, but he was clearly not there. So I had to be like, hey, can you turn off your audio? Anyways, it was pretty funny. But now I know how to mute everyone, so I learned something from that as well. Okay, cool. Oh, what are we doing today? All right, it's all kind of amounted to this. Okay. We're going to talk about linear programming today. Okay. So we've looked at how do we solve systems of equations. We're going to do that again, right? Linear programming just takes it to the next level. Okay. So a lot of the time, right, we're going to have a profit function, and usually, right, the more things we sell, the more money we make in kind of endless profit, right? Bless you. But in the real world, right, we have limitations like how many things can we produce, right? What's the cost of producing these things, right? And so we're not going to do any review because it's all going to come up in today's lecture, but also it was just on Monday, so hopefully you remember. Okay. So section 2.3 is on linear programming. I'm trying this easel again, but it's a little bit tricky. Okay. So we often have limitations or restrictions on our profit function. Okay. So we often have restrictions on our profit function. Right? Things like time, that's a biggie. Right? Time, materials, machinery, right? Labor, etc. Right, so those are all things that we need to consider in our profit function, right? We don't have just endless profits, right? We have these restrictions that we need to take care of. Okay, so linear programming, what we're going to do today, lets us maximize our profit function, right, taking into account these restrictions. Okay. So linear programming will let us maximize a profit function, given a set of restrictions. Okay. I'll show by example. Okay. So as an example, if we are given that the profit is 3x plus 4y, something like that, right? So the profit is given by 3x plus 4y. Okay. But we have these restrictions. So X is going to represent something and Y is going to represent something else, right? Maybe time and materials, for example, how much labor hours you have to the machinery you have, that kind of thing. So our restrictions are going to be that X has to be greater than or equal to 0 in this case. Y has to be greater than or equal to 0. These are kind of defaults because we can't have negative labor. We can't have negative time. There's a lot of things. We can't have negative most things, right? Most of these restrictions can't be negative, right? And so they all have to be positive, which puts us in that top right-hand quadrant of our graph, right? If we're thinking about our quadrants. So we're only going to be working in that top right-hand corner. Okay. But then I'm also going to tell you that X can't be more than 4. So it has to be less than or equal to 4. Okay. Also, bless you. And Y also has to be less than or equal to 4. Do you guys have your inequalities down? Right? The less than makes an L, right? X has to be less than or equal to 4. I'll just make a quick little note here. Less than or equal to. The greater than is the opposite, right? Doesn't make an L. So greater than or equal to. So if we map these restrictions, okay, we have some quadrant like this. We have our X and our Y axes. And then I'll do 1, 2, 3, 4. Just assigning those arbitrarily, right? And then same thing, 1, 2, 3, 4. I'm already ignoring the rest of the quadrants, right? Because I said that X has to be greater than or equal to 0. So I'll just do a, right? So it kind of is everything that way, or I guess I should point my arrow the other way. So those are all my X's, right? X greater than or equal to 0. If Y has to be greater than or equal to 0, right? That's all these Y's. Continuing. Y has to be greater than or equal to 0. Bless you. Oh, we've got an epidemic going on. It's the beginning of term. Everyone gets sick. So we've all been out and about in the summertime, and then we all come to the same place and everyone gets sick. It happens. So now we're saying that X has to be less than or equal to 4. So actually at 4 here, at X equal to 4, right, we can draw this kind of, oh goodness, I hit the button. I'll try not to hit it. All right, at X equal to 4, we've got a restriction, right? And we're saying that, all right, X has to be less than or equal to 4. All right, so it can only be on this side. Same thing with the Y has to be less than or equal to 4, so we can draw a line at Y equals 4. Oh, that got ugly. Trying to write on the side there. Okay. So y has to be less than or equal to 4, meaning that now we're restricted to everything below that line, right? And so here we're saying, okay, everything has to be below here. So really the only parts of the whole quadrant that we can work in, right? This is all the space that we can use, right? So that satisfies all our restrictions, right? X can't be more than 4, X can't be more than, or Y can't be more than 4, right? And they have to be positive, right? So we're working in this little, well, it's a square or rectangle or shape later on, okay? So these are all the possible XY combinations that we could use, right? Anything in that shaded area, those are all the possible XY values. But here's a fun fact. The profit is only going to be maximized at one of the intersections. So what we have to do is we have to find all the intersections and evaluate the profit at each of those points. And then we pick the highest one. Okay. So that's a little fun fact. An LFF, a little fun fact. Okay. The profit will be maximized. The profit will be maximized at one of the points of intersection. At one of the points of intersection. So going back up here, right, we're dealing with a simple square. It won't always be that nice, right? But we're just starting slow here. We have 4 points of intersection, right? We have this one here. We'll call it A. And then we have at 0, 4, we'll call it B. Should have used a different color, I guess. Then out here at 4, 4, we have the third intersection C, and at 4, 0, we have the fourth intersection D. I'll just highlight these with some green around, just for show. Okay. So here it's pretty easy. We see where these points of intersection are, right? That's not always going to be the case, right? That's why we had to learn how to solve systems of equations to find the intersection of two lines, right? And we'll do examples. Okay. But for this little guy, we'll just use these quick points. So just in general, how do we maximize the profit function? First thing we're going to do is just what we did. We're going to draw all the restrictions on the same graph. Okay. Draw all restrictions on the same graph. Okay. That's good. Next, we're going to find all the points of intersection. Find all the points of intersection. then what you're gonna wanna do is we're gonna make a list or a table of all those ordered pairs, right? Those XY combinations for all the intersections. So I'm gonna say, make a table of all the ordered pairs from part 2, right, or step 2. So make a table of all the ordered pairs from step 2. Step 4, then this is the point where we bring the profit function back in, right? The profit function's been off to the side until now. So now we have XY combinations, right? A series of them in a table. So now we evaluate the profit function at each of those XY combinations, and then we pick the highest profit. Okay? So 4, you're gonna calculate the profit at each of the points of intersection. Five, right? The largest or maximized profit, right, is what we call the optimal solution. I think we can all agree that maximized profit is the optimized solution. Okay. Also leading you into a field of optimization, which is a realm of math. If you want to go down that route, it's pretty cool. So the largest or maximized profit is the optimal solution. So going back to our little example here, right, we decided that we had 4 points of intersection, right, on our, this is called the feasible set. I won't use that terminology, but I did just now. So we're gonna make a table of all these points, okay? So A, B, C, D. Notice I labeled all my points. That's just to make sure that you're not missing one later, or right? It's nice to kind of see them all, okay? So A is at 0, 0. Oops, 0, 1, 0, 0. I'll put little colons. B was at 0, 4, right? That's scrolling over. C was at 4, 4. And D was at 4, 0. Okay. So I'll just label this at the top, the intersection. And then I'm going to remind myself that the profit was, I'll just steal it, 3x plus 4y. Okay. So the profit at A would be 0. I can almost guarantee that 0, 0 will never maximize your profit unless you've got a wonky profit function. All right, so 3 times 0 plus 4 times 0 makes 0 profit. So we know that's not our maximized profit. We can probably make a little bit more profit. Right? So moving on to 0, 4, right? We have 3 times x. X in this case is 0, plus 4 times 4, So 0 plus 16 is 16. Next one looks promising, right? 3 times 4 plus 4 times 4. 12 plus 16. 28. And then 3 times 4 plus 4 times 0. Which means that here, I'll do red. Maximized profit, right? Out of 0, 16, 28, and 12, 28 is the highest. Cool. So we can conclude that the profit is maximized at x equal to 4 and y equal to 4. Remember, x and y represent something, right? 4 workers and 4 machines, for example. With a profit of 28 whatever units. Okay. So that's pretty cool. Okay. Let's do an example that's not as nice. Okay. Right, this one was nice and tidy because we can just look and find the points of intersection. That's not always going to be the case, right? So if we have a look at example 72, the question will say maximize profit is x plus 1.2 y. And then the question will say something like subject to the following restrictions, right? So I give you a list of restrictions. The first restriction is going to be 2x plus y has to be less than or equal to 180. Okay. That's a nasty restriction. Second restriction is x plus 3y has to be less than or equal to 300. X has to be greater than or equal to 0, and y has to be greater than or equal to 0. Yeah. I don't know about you guys, but I've never really felt comfortable, or at least not when I had to do it myself, right? I never felt comfortable working with inequalities, right? Less than, greater than, whatever. But we can treat them as equal signs as long as you remember to flip the sign if you're multiplying or dividing by a negative. Okay? So let's make a quick note of that, right? Because it's nice to just be able to treat it as an equal sign and just ignore the inequality, right? And so we can treat the greater than, less than as an equal sign. But if we multiply or divide by a negative number, the sign will switch direction. The sign will switch direction. So how do we want to do this? So we have these restrictions, and we know that our first step, right, is to graph these restrictions on the same graph. Right? That's our first step. And then we're going to find all the points of intersection, but that's going to be easier to do if we can just visualize it first. So step one, graph the restrictions. Graph the restrictions on the same graph. Okay. Graphing these last two, that's pretty easy, right? They're just on our graph already, right? Working in that top right-hand quadrant. Okay. It's the first two that are a bit of a pickle. So just to shorthand it, I'm gonna label this 1 and 2. So to graph these, right, we're gonna, this is what we did last day, right? To graph straight lines. Here we have two straight lines, each of them only have x's and y's, right? And so we said, well, we're gonna solve for y, right? Get it into the form of y equals mx plus b. Right? And then we're gonna find 2 points on the line, plot those, connect the dots, right? So that's our kind of review of last day. Okay. So to graph 1 and 2, we need to solve each of them for y. Solve each of them for y. Technically, you don't need to, but it's going to make our life easier later on. Bless you. Okay. Then find 2 points on each line. So dealing with equation 1 first, right? We have 2x plus y has to be less than or equal to 180. Okay. So solving for y, we can do that still, right? Y is just on its own, so we have to subtract 2x from each side, right? We don't have to switch the sign because that's only if we're dividing or multiplying by negative, right? So now we're just subtracting from each side. So we say that y must be less than or equal to 180 minus 2x. Okay. Cool. How about equation 2? If we had to solve for y in equation 2, equation 2 was x plus 3y is less than or equal to 300. Getting y on its own now, right? We first have to subtract x from both sides. So we get 3y is less than or equal to 300 minus x. And then we have to divide both sides by 3. 3 is positive, so we're safe. We don't have to switch the sign. So y is less than or equal to 300 minus x all over 3. We like to have these guys in separate terms, right? mx plus b. So we can split that common denominator and say that, well, that's the same as y is less than or equal to 300 divided by 3 minus x over 3. Oops. Okay. Or 1 over 3 times x, right? That's the same thing. And then the 300 over 3, we can simplify even further, right? And say that y must be less than or equal to 100 minus, I'll keep it as x over 3. Okay. Oof, it's a lot of work. Right? So far, so good. So we've got both of these equations as y equals mx plus b, right? They're straight lines. Now they kind of look like it. Okay. So now we're going to find 2 points on each line. So line number 1 was, well, let's pick 2 values of x, right? We need at least 2 values of x, y, and I'm just gonna write it as y equals, right? Ignoring the inequality for a second. So y equals, oops, 180 minus 2x. So what are some nice x's we can use? My go-to 0, right? That's always nice. Because we're dealing with 180, maybe let's grab I don't know, a slightly bigger number. Let's do x equals 50. It doesn't matter. You could do 1 or 2 or whatever, but they're going to be really close together on the graph, right? So it might be hard to see them. So let's just trial and error, right? So I picked my 2 x's, and so my y here is going to be 180 minus 2 times 0 is 180. Okay. And then for my second point, my y is going to be 180 minus 2 times 50. 180 minus 100, 80. So I'm just going to sneak my ordered pairs on here. I'm at 0 and 180, and 50 and 80. Just nice to kind of jot them down somewhere. How about for the second equation? Doing the same thing, right? We have x and y, writing it with an equal sign. You can keep the inequality if you don't want to mess around with it too much. So y is 100 minus x over 3. Picking values of x again that we like, right? Not necessarily the same. Still like 0. I'll always like 0. Okay. So then we have 100 minus 0 divided by 3. Just 100. Now to get some kind of breadth here, I'm going to pick a bigger number, but let's pick a multiple of 3, right? To make our lives a little bit easier. Great. So we can do x is 60. So we have 100 minus 60 divided by 3, which is 100 minus 20, right? Okay. So writing out our ordered pairs again, just so we have them. We're at 0 and 100 and 60 and 80. Okay. So, all right. Now we have our points. And let me count here because I need 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to go up to 180. I'm going to go up by 20s for each line on here. Again, for the test, right, I'll give you the grid, right, so you don't have to make the grid. In fact, I'm going to try to make a grid this way. I need it bigger. Oh, it's game over. Oh, hey. I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. Hey, that's pretty cool. Neato burrito. All right. So just fill in 1 as my y-axis, okay. The other as my x-axis. Okay. I won't need nearly as much x as I do y, right? I already know that because looking at these pairs that I have to plot, right, the y's go from up to 180, right? Our x's, we don't need to go quite as far, right? They'll extend past 50 and 60, but we won't need as much room. But I'm gonna keep the same, so each line is gonna be worth 20 points, right? 20, 40, oops. 60, 80, 100, 120, 140. Couldn't have planned it better myself. Same thing on the x-axis, right? 20, 40, 60, 80, 100, 120. I'll fill in more if I need it. I'm gonna tell you right now, I don't. Okay, so we found points on each of these lines. So let's start by plotting the first line, right? We have a point at 0, 180. So 0, 180, let's do this here. All right. That's a point on line number 1. The next point on line number 1 is at 50 and 80. So 50 is going to be between these two, 40 and 60, and 80. So just like before, we're going to connect these two with a straight edge. So just take whatever you can find, get creative, and just, oh, it didn't take. Connect those two. And while I'm at it, I'm going to write that this is line number 1, which is y equals, bless you, 180 minus 2x. Okay. While we're at it, right, we can remind ourselves that the inequality is still there for line number 1. Y has to be less than or equal to this line, right? Meaning we're only concerned with, right, the less than area. So I'm actually going to change this. Right. Y equals 180 minus 2x, that is that line, right? But the area that we're interested in is all the area that's less than that line, right? So it's everything kind of below it in a sense. Okay. Cool. So that's line number 1. Now we do the same thing with line number 2. I'll try to pick a nice color. How about a deep green, hunter green. Not quite hunter, I guess. 0 and 100, right, is the first point on line number 2. So we're going to go to 0 and 100. And then the second point is at 60 and 80. So x is 60, y is 80. Close quarters here. That's just fluky. Okay. Same idea, right? We're going to connect these two lines with a straight edge. Yeah, it's totally possible that I skipped over, but I think I'm okay, right? Okay. So now I'm going to connect these two lines and extend the line. Nice. Okay. So this line, right, going back to our restriction, is y has to be less than or equal to 100 minus x over 3. So this line is line number 2. Y has to be less than or equal to 100 minus x over 3. Right? And because it has to be less than it, it has to be, so everything, only things below this line. So I like to kind of remind myself by putting little arrows on there. You don't have to. That's everything that we could use. Right? And then our baseline restrictions were that x has to be greater than 0 and y has to be greater than 0. We already assumed that because we only graphed the first quadrant, right? So it's all good. All right. Now, right, we have to find the points of intersection. Right? But first, let's identify the feasible set. Let's just call it what it is. The feasible set is the area that satisfies all the restrictions, right? So it's going to be all the area in from the lower corner up to all the lines, right? So that area there, that's the only area that satisfies all the restrictions at the same time, right? So that's pretty cool, right? So now we have to find all the points of intersection, right? And so it might be tempting to look at this, let's say, and say, oh, I can just kind of look here and figure out what it is. Here, you might want to look at that and say, oh, I can kind of tell what that is. No, there's going to be actual numbers. We know how to find where 2 points intersect. If you have 2 straight lines, we know how to solve the system of equations, right? Meaning find the point of intersection, right? So it's all kind of led up to this. And this is the whole goal of everything so far, okay? So let's identify all our points of intersection. Okay. So I'm going to start down here at 0, 0, call it A. Moving up the y-axis, I'll call this point B. Next, we have the intersection of our 2 lines that we drew, right? So we'll call that C. And don't forget where the first line crosses the x-axis, right? That's going to be intersection D. Okay. So we know A, right? A is at 0, 0. We know B, right? B is at 0, 180. Right? So we know those 2 points of intersection. We know A is at 0, 0. and B is at 0, 180. Pardon? Oh, is it one? Oh, sorry. Yeah. Thank you. It never happened. I was thinking of the top line. And B is at 0, 100. Thank you. But we need to solve to find C and D. Okay. But we need to solve, I'm going to throw it in there, the system of equations. The system of equations to find C and D. It's kind of on the angle now, so transition down here. It's more boring. Trying to train my wrist. Okay, so C, right? Point C is the intersection of line 1 and line 2, right? We can see that from our graph. So let's use that. So C is the intersection of line 1 and line 2. Okay. Here we can ignore the inequalities, right, and just use equal signs because we just want to find the intersections of those two lines. If you want, you can use the inequalities still, but if you're like me, I'm kind of keen to ditch them whenever I can. So I try to get rid of them. Okay, so line 1 was y equals 180 minus 2x. And line 2, just stealing it from my graph here, is y is 100 minus x over 3. So we solve systems of equations by substitution, right? And so what's nice is that they're both in terms of y. So I've already solved both of them for y. So that's what I mean in the beginning. It saves us a lot of time later on because we've already solved both for y. So I can plug 1 into 2 or 2 into 1, right? Basically set them equal to each other. Where they're equal to each other is where they intersect, right? That makes sense. Okay. So substitute, just following the same procedure that we did, right? I'm going to pretend to substitute equation 1 into equation 2. Right. So then I have equation 1 is y equals 180. So I have 180 minus 2x equals 100 minus x over 3. If you want to substitute 2 into 1, you can too. It'll give you the same thing, right? So basically you set them equal to each other. Okay. All right. I'll finish here to solve for x. Right. So now we have x's on both sides, so we want to collect like terms and eventually solve for x. Right. And so I am going to move my x's to the right and my numbers to the left, just because a quick glance here tells me that that's going to get rid of some negatives for me, right? And so, but it doesn't matter which side you move stuff to. Okay? So I'm going to have 180 minus 100 is negative x over 3 plus 2x. So now we have 180 minus 100. That's just 80. If you're like me and you don't want to deal with these fractions, I would pull out the like term, right? The x is the common multiple of both of these. So I'm going to pull out the x, actually factor out the x, ring a bell. It's all been to build up to this. So then we have negative 1 over 3 plus 2. To add or subtract fractions, hey, that rings a bell too. We have to get a common denominator, right? 2 is the same as 6 over 3. Okay. We could have cross multiplied, right? But this one's simple enough. So negative 1 over 3 plus 6 over 3. Now we can add these up. And so we get x, negative 1 plus 6, 5 over 3. Or you could just use your calculator. I don't really care. You can check with your calculator too. Notice if nothing's really changing on the left-hand side, sometimes I'll just stop writing it out, right? And just keep the equal signs. As long as I'm stacking the equal signs, I can do that, right? So the 80s just stayed the same, right? So I just kind of keep the equal signs there. I'll pull it back in when I need it. So I'm saying that 80 is 5 over 3 times x. To get x on its own, right, I technically have to divide both sides by 5 over 3, right? Or I can multiply both sides by 3 and divide by 5, right? Either way you do it, you end up at the same thing. So you get x is 80 times 3 over 5. That's legal. So then I get 80 times 3 divided by 5. Nice, clean 48. So if x is 48, right, then we can check here and say, oh, that looks reasonable, right? That's a good first thing to check. Did what I find actually make sense, right? It looks like it's about at 48, right? And so that's a good start. And then now we're going to find y, right? We actually have 2 equations for y. I'm going to use equation 1 just because it's nicer to look at, right? And so now substitute x equal to 48 into equation 1. Equation 1 was, if I can remember it here, y is 180 minus 2x. So it's 180 minus 2 times 48 times 2, negative, plus 180. Oh, 180 minus, I think it was 96. 84. Yeah. Therefore, C, right, is at x equal to 48 and y equal to 84. Right? So notice you can't just look at our graph and say, oh, I know where those points are, right? Because you wouldn't be able to see it so precisely. Right? So we have to do the work. All right. Now we're gonna find point D, right? Point D is the intersection, right? So where line 1 crosses the x-axis, the x-axis is where y is 0, right? So to find D, right, we need to find where line 1 crosses the x-axis, which is just the line at y equals 0. Right? Okay. So our system, right? So essentially we have to solve the system line 1, which was y equals 180 minus 2x, right? And y equals 0. As long as we remember that the x-axis, right, is where y equals 0. That's the line there. Okay. Oh, this looks much better, right? Here we can solve for x. We know that y is going to be 0. Oh yeah, sorry, question? Perfect. Question? No? Okay, I thought I saw it. I'm trying to be on the lookout down here. Hello. All right, so the same idea, right? Shouldn't recycle my numbering, but I will. Hopefully it'll, oh, okay, fine. 3. Because I think that first one's been line 1 all along, right? So substitute equation 3 into equation 1, or if you want to just say setting equation 1 equal to equation 3, that's the same thing. Right? To solve for x, right? We get that 0 equals 180 minus 2x. I'll move my 2x over to the left-hand side, right? So add 2x to both sides, so I get 2x is 180. So x must be 180 over 2. X must be 90. And we already know that y is 0, right? So therefore, intersection D is at x is 90, y is 0. Okay. So now we have all our points of intersection. Now time for the fun stuff. Now we can make a table of all our intersections. Right? Make a table of all points of intersection. Easy to forget, right? But the whole goal is to maximize the profit function. We've already forgotten what the profit function is, right? But we'll remind ourselves in just a second. But first, let's make a table of all these points of intersection. So I'll start here. Intersection, and I've labeled them A, B, C, and D. A was at 0, 0. B, we said, was at 0, 100. Once I corrected myself. C was at, thank you, 48, 84. And D, 90, 0. Cool. So now we can add to this table here. And now we have to scroll back and find what our profit function actually was. It was way back here. Oh, too far. Where was it? Da, 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 da. Oh, here we go. X plus 1.2y is our profit function. So it doesn't come into play until the very, very end. Right. I'm just going to copy this so I don't forget it. And so I don't mess it up. That happens, you know. Sneak that in there. So the profit is X plus 1.2y. All right, nothing to it but to do it, guys. Here we go. So the profit at intersection A would be 0 plus 1.2 times 0. I'm going to take a wild guess and say it's 0. Right? How about at point B, we have 0 plus 1.2 times 100. Still pretty reasonable. Let's call it 120. How about point C? X is 48 plus 1.2 times y, which is 84. I'll use my trusty calculator here. 1.2 times 84 plus 48. I get 148.8. What do you guys got? Cool. That looks good. And then my point D is going to be X is 90 plus 1.2 times 0. It's just 90. So we did it. Out of 0, 120, 148.8, and 90, 148.8 is the maximized profit, right? And so the profit is maximized when X is 48 and Y is 84. Right? Everything else in that box that we drew initially is just going to yield lesser profit. So this is maximized profit. Woohoo. And we like it. Therefore, the profit is maximized at X equal to 48 and Y equal to 84 with a profit of 148.8. We don't know units and they don't matter in this case. Oof. So there's definitely going to be one of those on the first test, right? They take a long time, I know that, right? But I think as long as you're methodical about it, then it's going to get easier, right? So it incorporates, I like testing this because it incorporates basically everything that we've learned so far, right? Drawing straight lines, solving systems of equations, right? Just factoring and working with fractions often, right? All those things are kind of incorporated here. Okay. Any questions about it? I know it's a big thing. All right. Cool. All right. So these examples take a long time, so we don't really have time for another example. But I do recommend that you try some in the textbook, right? And working through them. Yeah.
How much work do you want us to show?
Basically, unless it's a little side note in here, basically all of what we did here. Yeah. Just to be safe, just write out your whole thought process. right? It's your goal to show me how much you know, right? And so the more you can give me, the better. Right? The safer, I should say. Okay? So practice those, right? We'll do, it'll be in the review before the test. So we'll see a few more, right? But for now, we're going to move into chapter 3. Okay? So that's the end of chapter 2. And now we're into chapter 3. Chapter 3 is business economics. Kind of a broad stroke if now that I think about it, business economics. Wow, that's so precise. Okay. And I want to kind of get this over with. We're going to delve into calculus and then step back a little bit, okay? So just like a touch of calculus today, and I'll show you the shortcuts, and then no more calculus, okay? What I like about today is after today, we'll get more focused on the material, right? So this is kind of the last piece that we have to get done, and then the rest we can kind of settle in, focus on stuff. Okay? So bear with me. 3.1 is what we call the basics, I guess. I'm going to call it an introduction to calculus. Now, if you've taken calculus, that's great. If you haven't, that's fine too. Okay, not to worry. Who has taken calculus, by the way? Cool. Great. We're just going to do derivatives of polynomials, in case you know what that is. So you can all breathe a sigh of relief. They're not going to be that bad. Okay. So let's start from the beginning. Maybe this will inspire you to take calculus as an elective, I guess it would be for you guys. It doesn't sound so good. So calculus or derivatives talk about the slope of the tangent line. So in the form, right, in the form y equals mx plus b, right, we know that m is the slope. And from probably high school, you probably remember that the slope, we remember it as the rise over run. So if we have something set up, right, x and y and just this kind of arbitrary function, f of x, right, that's our function. F of x is the same as y. Y equals mx plus b is the equation of a straight line, right? So here we have it. And if we put in an x value of a and x value of b, right? A yields f of a and b yields f of b. Right? And then we're told that, okay, the rise, right, is the distance between these 2 points, right? Or the rise between f of a and f of b. Okay. So the rise is f of b minus f of a. And then the run, right, is the distance between a and b. Run is b minus a. we take our biggest values minus our smaller values. Which means that we can rewrite the slope as f of b minus f of a over the run, which is b minus a. Okay. Now, if this doesn't make sense, don't worry, because I'm not actually going to use it. I only wanted to cover it because if you're reading the textbook, right, then you'll need to know this stuff because it explains it a little bit more thoroughly. But that's the idea of it. Okay. So the first course in calculus is about derivatives. Okay. So a derivative is the slope of a tangent line at some point x. Okay. So the derivative is the slope of the tangent line of f of x at some point x equal to a. It doesn't matter what x is. Okay. So what's a tangent line? A tangent line is a straight line that touches only one point of the curve. So for example, if we move away from straight lines and we have some f of x that looks kind of like this, right? Here's our new f of x. Okay. Then at this point here, let's say, at x equal to a, we have some straight tangent line that only touches that one point. Right? So this is the tangent line. Okay. So the tangent line is a straight line that only touches a single point on the curve. Okay. Meaning that each possible value of x, right, an infinite number, will have its own tangent line, right? So it's gonna just kind of move along the line there. Okay, so each value of x will have its own tangent line. So now, if we go back to the derivative, right, the derivative of a function is going to give us the slope of the tangent line technically at any point of x. Okay. So finding the slope of the tangent line, this is all kind of leading somewhere, don't worry, but it's going to take a while to get there. It's going to be helpful to know the slope of the tangent line. Okay. So I'll just rewrite it because it's good to have. Okay. So we said that the derivative of a function, remember a function we denote f of x, is the slope of the tangent line and the beauty of it is we can develop the function for the derivative, right, the slope of the tangent line, and then we can find the slope of the tangent line at any point of x. Right? So is the slope of the tangent line at any value of x? So essentially, right, it gives us a function for finding the slope of the tangent line. Okay. So it gives us a function for finding the slope of the tangent line. The tangent line. Okay. So for notation, right, we need some way to denote the derivative of some function. Right? So we denote the derivative of f of x being our original function, by f prime of x. Okay. So we read this as f prime of x. Okay. Or whatever the function is called, right? We've been dealing with profit functions, so we could find the profit prime of x would be the derivative of the profit function. Or if we have a profit function, which is what we'll be dealing with, a profit function, we denote the derivative as the profit prime of x. Right, so just throwing in that little apostrophe says that this is going to be the derivative. Yeah. So we've talked about polynomials before, right? Just ever so briefly, right? But we only need to be able to take derivatives of polynomials. So I'm not actually going to go through and show you the technicalities behind it. I'm going to show you my shortcut, which involves just nudging your equation a little bit. Things fall down, you multiply them, and you move on. So let's start with, so we need to be able to find the derivative of a polynomial. A polynomial is something, so it's a function, it's f of x where you have some coefficient a sub n. That's just to denote that you can have as many as you want, right? As many terms as you want. A sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1 plus a sub 1 times x to the 1. Technically, you wouldn't really write the x to the power of 1, just x, plus a sub 0. In real life, it would look something like f of x might be 3x to the 4 plus 6x to the 3 plus x squared plus 3. right? We've seen things like this before, right? Where we had to collect like terms, right? And factor or expand and simplify, right? So we've dealt with polynomials just briefly. Okay? And we said, oh, it's a good idea to sort these with the descending powers of x, right? And that's because we call this a polynomial of degree 4, because our highest power of x is 4, right? So just as a little note here, this is a polynomial degree 4, because the highest power of x is 4. The highest power of x is 4. So we need to be able to take something that looks like that, right? 3x to the 4 plus 6x to the 3 plus x squared plus 3, right? And we need to be able to find the derivative. Now, like I said, there are technical ways, obviously, it's math. But what I'm going to teach you, because it's, I think, way faster, is you imagine just kind of giving your function a bump from the right-hand side, and all those powers, they kind of fall down in front and multiply its coefficient, and then the powers are decreased by 1. We'll do some examples, and then you'll say, oh, that's it. So don't worry. Okay, but let's make a note here. So of course, there are technical ways. I don't want you to walk away thinking that that's it. There are technical ways of finding the derivative. Okay. But to find the derivative, of a polynomial, okay, I imagine giving my function a bump from the right-hand side making all the powers of x fall down to multiply each of the coefficients, right? Fall down to multiply the coefficients and the powers decrease by 1. Bless you. Decrease by 1. Okay. So as an example, right, let's use this f of x that we had before. So f of x is 3x to the 4 plus 6x to the 3 plus x squared plus 3. If I want to find the derivative of this, right, I'm going to say that f prime of x, right, that's the derivative of f of x, is going to be, so I give my whole equation a bump, right? And so I keep my 3 here, but the 4 bumps down in front, right? So those coefficients get multiplied. And then I have x to the power of 4 minus 1 up top. Right? So it decreases the highest power by 1, or all the powers by 1. Okay. Plus 6 times 3, right? That 3 falls down in front, times x to the power of 3 minus 1, plus the 2 bumps down in front. Technically, there's a 1 there, right? 1 times x squared, but I'll ignore it. So I just have 2 to the x to the power of 2 minus 1. Okay. Technically, right, we have 3 times x to the power of 0. X to the power of 0 is just 1. Okay. And so any constant value like 3 that isn't attached to an x, right, that's just going to go away once you take the derivative. Okay, because if you bumped 3x to the power of 0, the 0 bumps down in front, and now it's gone, right? So technically plus 0. Okay. We can simplify this, right? 3 times 4 is 12 to the x to the power of 3 plus 6 times 3, let's call it 18. And x to the power of 2 now, plus 2. 2 minus 1 is just 1. We don't write the 1. So that's it. Okay. So the derivative of f of x is 12x to the 3 plus 18x squared plus 2x. Okay. In general, if you want to know in general, so in general, if f of x, right, was a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus where did I cap it? A sub 1, oops. A sub 1 to the x to the power of 1 plus, thank you, plus a sub 0. That's a polynomial in general, right? Any polynomial. Then f prime of x is going to be a sub n times n, right, times x to the power of n minus 1 plus a sub n minus 1 times n minus 1 times x to the n minus 1 minus 1, so minus 2, right? Plus a sub 1 times 1. X to the power of 0 we said was just 1, right? I'll make it here. Plus 0, because we already talked about that constant a sub 0 just goes to 0 once we take the derivative. So you can use this too, it's fine. But I like just giving it a bump. Everything falls down, decreases by 1, and then you're done. So looking at this kind of nicer one, the 12x to the 3 plus 18x squared plus 2x, this itself is a function, right? So now we can plug in any value of x and find the derivative at that point, right? The derivative is the slope of the tangent line, right? So once we have found f prime of x, right, we can find the slope of the tangent line at any point of x. So if we recall that so if f prime of x, just the one that we did earlier, was 12x to the 3 plus 18x squared plus 2x. Okay. Find the slope of the tangent line at x equal to 2. So now we're going to find f prime at 2. Okay. So 12 times 2 to the power of 3 plus 18 times 2 squared plus 2 times 2. Dealing with my powers first, right? Being careful there. I get 12 times 8 plus 18 times 4 plus 2 times 2 is just 4. So I get 96 plus 72 plus 4. 172. So the slope of the tangent line of the original f of x, right, at x equal to 2 is 172. Pretty steep, right? So we've got kind of a quick increase, right? Rise over run. Oh, why do we need this? Why do we even need this, Emily? Well, let me tell you. There are some scenarios that we'll be interested in where we have the profit on the x-axis, or on the y-axis, sorry. And the profit function might look like this. So there are cases where the profit function looks like this. So if I tell you that this is the profit function, profit of x, I shouldn't do that because it's on the x-axis. I'll put it up here, the profit of x. Right, that's your profit function. So you've got some increasing profit, and then you hit a peak, and then all of a sudden you're getting a decrease in profit. We don't want that, right? So you don't want to be producing too much. This is a monopoly scenario, usually. Okay. And that's why we're sort of interested in it, right? But it's just another way to maximize our profit, okay? Because we can see here, right, that at this point, at the peak, that's our maximized profit. Okay. So in this case, the profit is maximized at the peak of the function, right? So at the peak of the function, as a fact, okay, at any high point or low point, right, where, or any kind of point like that, what did I get? Oh, fun. Another one. I have to turn off my notifications. I did my messages, my Messenger, my Snapchat, my Instagram. Forgot. Yikes. So what was I saying? Oh yeah, so at this peak, okay, just as a fact, at the very peak, the slope of the tangent line is going to be 0, right? Because it's just touching that top peak, right? And so the slope of the tangent line is 0. That's cool. We know the slope of the tangent line is the derivative. So that means we can just set the derivative equal to 0 to find the maximized profit, right? And so here, right, this is going to map down to some value of x, right? And the tangent line here right? So just as a fact, the slope of the tangent line, right, where the profit is maximized, will be 0. Okay? So the slope of the tangent line where the profit is maximized will be 0, right? Because if you're thinking about a straight line like this, right, you've got your peak and then you've got your straight line here and it's completely horizontal, right? If you're thinking rise over run, there is no rise, right? The rise would be 0. 0 divided by anything is 0, right? So the slope at that point is 0. So we use that fact to maximize the profit function. Okay, so we use this fact to maximize the profit function. Okay. So it'll go something like, given a profit function, we have to find the derivative of it. Okay. Find the derivative. Once we have the derivative, and we're only going to be dealing with those really quick functions, right? Those polynomials. So once we have the derivative, we set it equal to 0, right? We force the derivative to be 0, and then we can solve for x, right? What x makes that derivative 0, right? So then we set the derivative equal to 0. Oops. And then step 3, solve for x, right? This value of x maximizes the profit function. This value of x maximizes the profit function. Right, so that's the value of x that maximizes the profit function. Once you have x, you can find what the maximized profit would be, right? You plug in that x into the original profit function. Using the original profit function, we find the maximized profit oops, that says by by substituting the x from step 3. Cool. So what are these questions actually going to look like? Right? They won't be that bad as long as we remember these steps. Right? So just as an example, example 77, I'll say let f of x be negative 5x squared plus 250x minus 500. And I'm just going to say maximize f of x. Right? Or the function could be a profit function. Okay. So, right, we have f of x, but it could be profit of x, it doesn't matter, right? And then maximize this function. So I'll just rewrite our function here. So we have it, f of x is negative 5x squared plus 250x minus 500. Our first step, right, is to find the derivative of this function. So f prime of x, so we give it a shove, the 2 drops down, decreases by 1, and then, so we have negative 5 times 2, x to the power of 1, right, plus 250 technically times 1, but a nice thing about if you just have an x, like a coefficient times x, you're just left with a coefficient, right? So you just have plus 250, and then just the constant minus 500 disappears completely. So you've got this kind of way nicer, easier function in your derivative. So f prime of x must be negative 10x plus 250. That's great. Now we know that this function is maximized when the slope of the tangent line is 0, right? So we set the derivative equal to 0. Set derivative equal to 0. So we have 0 equals negative 10x plus 250. And then I guess set derivative equal to 0 and then solve for x. I'll squeeze that in there. Solving for x. I'm going to move my negative 10x over to the left-hand side, make it positive. So I have 10x is 250. So x is 250 over 10. So x is 25. We're almost there, right? But don't stop yet, because this is the point of x where f of x is maximized, right? But we want to maximize f of x. So we want to know what is f of x at x equal to 25, right? So, but I will say, therefore, f of x is maximized at x equal to 25. Okay. So f of x, remember, was, where did I have it here? I'll just copy from here. Negative 5x squared plus 250x minus 500. Okay. So f of 25, using our notation that we learned, oh man, it's all coming together. F of 25, negative 5 times 25 squared plus 250 times 25 minus 500. Dealing with my exponents first, 25 squared. Thank you. So I get negative 5 times 625 plus 250 times 25 minus 500. You could have simplified there. That's fine. I just like to keep them all. Negative 3125 plus 250 times 25. 6,250 minus 500. So I get 3125 negative plus 6250 minus 500. 2,625. Okay. So f of x equal to 2,625 is the maximum, and it occurs at x equal to 25. Cool. So we did a lot of theory, but in the end, this is all we really have to do, right? I give you a function, right, a profit function, and then we have to find the derivative, set it equal to 0, solve for x, plug it in, and we're done. Any questions before you all leave? Yeah. Oh yeah, I will be posting a Moodle quiz just to get everyone on board. Okay. So look out for that. I'll give you a week to do it. We'll talk about it later. Yeah. All right. Have a good weekend, guys.